Okay, now recording again.
That would
Hey,
have been
hey,
wild.
hey, graph theory friends. I almost didn't start recording, but I did. Uh, cool. So this is week 2 of graph theory. What should we call this? Like graph theory for beginners? Like graph theory, all you need is graph.
Yeah. All you need is graph. Graph. Um, it's the it just doesn't really sound like anything. It's not really kind of a word. Graph. Riff
Yeah,
graph.
graph. What about
Mm.
graph theory, colon, not that kind of graph?
Oh.
I'm
Okay.
not that I'm not that kind of graph. An introduction to graph
Not that kind
theory.
of graph. Yeah. Graph. Uh, graph feats.
Ooh.
E.
Work in progress, work in progress.
Mm.
Cool. So,
We can edit this
yeah,
video.
we can edit this video. Well, if I was less lazy and hadn't lost all my video editing software when I bought a new computer, then I would.
We can add a good. We can add a good idea in post.
Yeah, exactly. Yeah, I think the new Premiere Pro has a function for that. Good idea option. Um,
Perfect.
Cool. So I guess like we could. I originally was like, oh, we'll kind of like review some stuff from last week at the start. But I feel like because you like did that homework thing during the week, and like it's probably like reasonably fresh in your head from that. I'm guessing.
Yeah, I also did the first problem, the maze thing from the
Oh,
worksheet right before
cool.
this, and I also put some graph theory to work in conceiving a new project this week.
Oh my god, tell me about that.
I'll make it very brief because we should get started, but it's like
True.
oh, let me see if I can like import an image. Oh, search for an image. No, that's not what I mean. Can I image library? Yeah, allow access to all photos. I'm gonna regret that, but whatever. Albums. No, I don't have it. Okay, whatever. Basically, it's about like, so the show that I wrote the scene in that you saw, I was like, what
Mm.
if you did a massively expanded version where all of those people then like go off and have other scenes with other people? And I was trying to map like
Oh
what the
yeah, yeah, yeah,
network of
yeah,
connections between characters would
yeah.
be.
Wild.
Um, and I did this big drawing of a graph of it, and then I used graph theory to calculate the number of scenes rather than
Oh my
manually
god.
counting them.
Wow, I love that. So applicable. Who
Mm,
knew? Planning plays,
yeah.
settling Mars, useful for that.
Settling
Yeah,
Mars. Yep. Social
yeah,
dynamics of settling Mars. It's popping up
yeah,
everywhere.
yeah. Wow, there you go. I'm aware that
Mm-hmm.
we're starting more than slightly after 8. Um, what times
Mm-hmm.
what time would you like to make sure that we are done by?
um, is 10 possible?
Yeah, anything's possible.
Okay, just because I have an 8-hour day in studio tomorrow,
Oh, yeah,
and
yeah,
I have to
yeah.
be up at 6:30. So,
Yeah, yeah, yeah. Cool.
mm,
Alrighty. 10 it is. Let me just reset this timer. Uh, oh no, that'll work. Cool. Okay, yeah. So, I guess yeah, we can get into the new vibes. So,
yeah.
first thing this week, there's like the start of this is gonna it's just gonna be a bunch of like um basically like different types of graphs, like names for types of graph type of thing. Or like for
Mm-hmm.
like terms or like graph related concepts. So it'll be like, here's an example of this
Mm-hmm.
thing, like here's the definition, this is what it's called, and we're gonna do
Mm-hmm.
like a bunch of those. Um,
Mm-hmm.
yeah, so less like proving things at the start. We'll get into a bit of that after this. It's gonna be like a whirlwind
Mm-hmm.
tour, a whirlwind graph
Mm-hmm.
tour. Yeah, cool.
Cool.
Okay, so the first thing is cycles. So
Cycles.
yeah, so if we draw a graph, uh, too bad this isn't one of those fun real graphs. Uh, anyway,
It's too bad it's not what?
Too bad it's not one of those fun real graphs. Um, so like the the search party graph, etc. The famous search
Oh,
party graph
sure.
on which many
Yeah.
papers have been written. Um,
Yes.
that's one of the types of graphs we'll be addressing today. Um,
Uh-huh.
so a cycle. So like the different colors. Great. Oh, no, I guess I can do that laser pointer thing. Where was that? Is that down the bottom? Great. So this.
Yeah.
Oh, that is a cycle. um, that is a
Mm-hmm.
cycle.
Mm-hmm.
Um, uh, hang on, I got to make a better example of a not a cycle. So
Well, this part would be not a cycle, right?
that is not a cycle, correct?
Yeah.
But also that is not a cycle. Um,
Hang on, there's a
because
Oh yeah.
maybe the laser
Okay.
pointer is yeah, because you hit ooh, um because you like hit a vertice twice before you get back to the start.
Uh-huh.
It like crosses
Mm-hmm.
over itself, I guess is a way you could think about it.
Yeah.
Um,
Cool.
yeah. So the definition of a cycle, let's see if I remember this, is so it's a walk. Actually, I guess we need to find other terms in order to define cycle. So a walk is if you take the definition of a cycle and then just make it very permissive. So like this is a walk, that's a walk, that's a walk, anything's a walk. So
Yeah, sure.
a walk is just a set of vertices and the edges between them. I guess a way. A set of vertices. Uh, sorry, a sequence of vertices. So like that's the first, then that, etc. Um, and edges such that the first edge connects the first and second vertice, the second edge connects the second and third vertice, etc. And
Mm-hmm.
you can have repeated vertices and edges and stuff. That's all fine. Um,
Mm-hmm.
yeah. So it's just a yeah. So I guess if these are like cities and railways between them, it's like any rail journey could be. There's no conditions on it.
Yeah.
Um, and so that's a walk. And a cycle is a walk uh, which switch to text now. Oh, this is the awkward bit. Sure. Let's switch to text. A cycle is a walk. So it's like V0. That's like that little. The underscore means like subscript. It's like how most people
Mm-hmm.
write subscripts when they can't do subscripts. So you got like V1,
Uh,
V0, V1, etc. Oh, up to Vn. And Vn equals V0. So it's the same. So it ends on the same vertice that it started.
mm-hmm.
Um, Vn equals V0. Uh, and Vn and all the vertices are distinct. Yeah. So none of the Vi, no two of these vertices are the same, except for like everything from V0 up to Vn minus 1 are all different from each other. Yeah, I think that's right.
Cool.
Oh, and it also has to have n has to be at least 3. So uh yeah, it can't just be like you can't have a cycle that is just like a vertice because it starts and ends on itself. It has to at
Yeah.
least be boom, boom, boom. Is the smallest cycle. Yeah. Um, and then
Cool.
we call that so whatever n is like if n is 4, then you call that a 4 cycle. Or for this triangle here, n would be 3 because you have 0, 0, 1, 2, and then 3. V3 equals V0, and so that's a 3 cycle, etc. That's a 4 cycle. Yeah.
Cool.
Right, so
Very
that
good.
is cycles. And then, uh, any questions about cycles?
Nope, so far so good.
Great. Let's meet our next graph concept, which is so you could walk. Great. So our next concept is are regular graphs. So mm, hang on, I'm just gonna check that I didn't get something wrong in the definition of cycle because now I'm nervous. Uh, cycle of like the overlapping stuff. Uh, uh, cycle of walk which can go in 0 then that's a par. Yeah, exactly. Cool. Yes, this was correct. Um, yes.
Yay, we did
So,
it.
yay, did it. Erase this stuff. Fine. So what did I say? Ah, regular. Great. So, draw a graph. How many vertices should we have in this graph?
7.
7. Okay. 1, 2, 3, 4, 5, 6, 7. So a two regular. To make this graph two regular,
Mm-hmm.
mm, this is two regular because each vertice has a degree of 2.
Sure.
And say this is a separate graph over here. We have a graph with 4 vertices. If this is
Mm-hmm.
3 regular, then it would look like, well, I guess it would actually be complete. It's 3 regular. Yeah.
Yeah.
Yeah. So um, R regular just means every vertice in the graph has degree of R.
Cool.
Yeah. And fun fact, as you can see here, that this two regular, well, maybe you can, if you imagine things kind of untwisting a bit, that this two regular graph is actually a cycle. Can
Mm-hmm.
you see this side?
Yeah.
Yeah. And every two regular graph is either a single cycle or is a set of disjoint cycles, meaning, for example, you could have disjoint just means like they don't share any vertices. So you could have a graph
Mm-hmm.
which is like, because like we were saying last week, graphs can be in separate parts. So you could have a graph which is just like
Mm.
two separate 3 cycles or something. Um, so any two
Yeah.
regular graph is just some set of cycles, separate cycles. Yeah. Cool.
Mm-hmm.
So that's our regular.
Cool.
Next graph concept. And then we're gonna do some questions that use these and a bit of stuff. Just going through them. Next graph concept is subgraphs. These are kind of fun. So draw a graph.
I'm gonna draw a graph.
Yeah.
Okay, great. Let me see. Good. That's a cool color. Go. Mm-hmm. There we go.
Love it. So
I think there's a bit of a delay, by the way. So
okay.
mine's like a triangle with a tail, and then there's a vertice that's not.
Cool.
It's got degree of 0.
Yeah. That came through, I think, pretty quick. So I'm
Cool.
going to now draw a subgraph. So I'm like drawing another graph. Kind of over the top of this. Well, not really. Like the things that I'm highlighting in green, I'm like referring to those vertices or edges. So if we take this vertice and this vertice and this vertice and this edge, that's a subgraph
Uh huh.
of that graph. Or I could do another subgraph. which is just this. So it's just any graph which has where this new graph, the subgraph, its edges and its edges are a subset of the edges of the first graph, and its vertices are a subset of the vertices uh, of the main graph. Sorry, I meant of the main graph of the first as well. So you're choosing some or all of the vertices and edges of the first graph. But obviously you can't like take an edge without both of its vertices because then it wouldn't be a graph. So the subgraph still has to be a graph, but as long as it
Mm-hmm.
meets the definition of a graph and only has vertices or edges that are in the first graph, then it is a subgraph
Mm-hmm.
of that graph.
Cool.
Yeah. So like if this is
Great.
some friendship circle, you can be like, well, we're just going to take these friends and their connections or whatever. But
Mm-hmm.
you can also leave out certain connections, etc.
Uh-huh.
Yeah. So I guess like say we were talking about the Friends TV show graph and how like the Friends TV main characters of Friends who like and their connection is knowing each other. That's a complete graph, but that like our
Mhm.
friends is not a complete graph. So the like our
Yeah.
friends graph would be like a subgraph of the like knowing each other graph.
Yeah,
Yeah.
cool.
Yeah. Cool.
Love it.
Uh so that's a subgraph. Then um And there's another concept which is kind of useful, which is an induced subgraph. And what that means is, I'll just undo these. An induced subgraph is you just choose a subset of the vertices. Subset meaning uh, anything from zero of them to all of them,
Mm-hmm.
and then you include every edge which connects two of the vertices in this subset. So like this would be the induced subgraph for those three vertices. Um, Whereas if we didn't have that edge, then it would not be an induced subgraph. Like this is still a subgraph, but an induced
Mm-hmm.
subgraph means so it's like you take some of the people. It's like if you have a graph of a big social group, and you're like, okay, we're just going to look at these five people, and their connections, but you have to actually include all their connections. Whereas in it's just a general subgraph, you have discretion over which edges you want to include or not.
Yeah.
Yeah, does that make
Cool.
sense? The distinction.
Absolutely.
Cool. So that's induced subgraph. Uh, then we'll go to a concept I feel like has come up maybe even just last week because I don't know if you used it by name, but maybe be familiar. When we were talking about the fact, when you were coming up with the examples of graphs that are kind of maybe edge cases or like, would this count as a graph before we did the strict definition? I think like
Mm-hmm.
one of the ones we talked about was something that kind of looks like multiple graphs. And I might have mentioned that that is a disconnected graph.
Mm-hmm.
Um, Whereas if we do that, then it becomes a connected graph.
Mm-hmm.
So if we want to make that precise and give it a definition, the way we can do that is, well, uh, how might you try to make that precise with the definition of what? Because we obviously get the vibe. It's like, yeah, this seems disconnected. This seems
Mm.
connected. If you had to like say mathematically, or to someone who didn't get it from the vibe, how might
I
we
would
do that?
say a connected graph is one in which there is a possible walk which connects all vertices, and a disconnected graph is one in which
Oh,
there is not.
love that, love that. And that is basically how we do it. I guess there's like one ambiguity in what you're saying, which is when you say connect all vertices. Um, yeah, what do you mean by that?
Uh, should I say a walk upon which all vertices are? What's that word I keep
Oh, like
forgetting?
which contains all vertices? I guess you could say. So like you do a walk and all vertices are on that walk.
Yeah, or like
Yeah.
what's that thing the edges are
Oh,
incident
incident?
upon? All the
Yeah.
vertices are incident upon the walk.
I think the term would be yeah, which contains. You talk about it containing. Yeah.
Okay.
Yeah.
Okay,
Yeah,
sure.
interesting. So I'm just thinking, uh, yeah, that's slightly different to the normal way of defining it, but I think it's equivalent. Like I think it's the same. It means the same thing,
Mhm.
but it's just expressed differently. Yeah, because the
Okay.
usual way we express it is to
Cool.
say that for any two vertices, there is a path between those two vertices. Um, a path
Hmm.
just meaning um, a path is like a walk where you don't repeat any vertices. In fact, it's not like that. It is that. So, so like that is a path, but like that is not a path. Um, yeah.
Cool.
But yeah, I'm pretty sure that that would be equivalent. That if you have a path between any two vertices, then it's going to be possible to make a walk which includes all vertices because you just keep all the vertices you haven't, all the vertices that you haven't included yet. You can just then add on at the end the path to that vertex and then the path to the next missing vertex, etc. And you're going to have a walk which includes them all. Yeah,
Mm.
cool, great. So
Great.
there you go. You have defined this. This is a connected graph. Um,
Hmm.
the I guess like yeah, maybe there's something in like the saying a path between any two vertices is maybe like a handier one to use when you're proving things, but I'm not even certain of that. But I guess yeah, just keep that one in mind as well, in case that is
Sure.
handier. Cool. Then okay, this is also fun. So, um, oh,
This animation where the like chalk dust coming off when you erase stuff is
oh,
wild.
I don't think I got that. I'm not getting that.
I'm
Or
getting
did I
that
just
on
miss
my
it?
iPad. It's like you're like erasing
Clear
from a white
frame.
from a blackboard.
Oh yeah, I don't get it. Damn it.
Okay. Well, fun for me.
Yeah. So, cool. So we've got. Mm, oh, I can do this. So in the graph, in the railway graph, I'm going to do the cities. See if I can do it from memory. Hobart, Hobart, and we got Melbourne, which connects to Sydney, and they also both connect to Canberra, and Melbourne connects to Adelaide, which connects to Perth, which connects to, and Adelaide also connects to Darwin, and then
Hmm.
Sydney connects to Brisbane. I think this is. Wait, have I forgotten any cities? I think I've
I
forgotten
seem
something.
to recall that there was like one more
Yeah,
horizontally typed line.
I remember
Like
something.
either there's a Darwin to
Let me have a
Brisbane
look.
connection maybe, or
Yeah, let me pull up this graph. Gonna know the Australian rail system so well after. Let's
Mm.
see. Real graphs. Uh, do, do, do. Just loading. Oh, yeah, what have I. Yeah, Adelaide also connects to Sydney. That's the one. So
Aha.
we have this vibe. Cool. So, in this graph, I'm going to point out the things which are bridges. So this edge is a
Mhm.
bridge. This edge is a bridge. This edge is a bridge. This edge is not a bridge. This edge is not a bridge. None of the other edges are bridges. Uh, do you want more? Oh, maybe this is a fun way to do it. Like, you can either like request another example or be like, oh, I think I know what a bridge is. Here's
No,
my
I
guess for
know
what a
what a
bridge
bridge
is.
is.
Okay, great. What's a bridge?
It's like when there's two bodies of land and there's like no, sorry. A
Yeah.
bridge is no, it's any edge that is incident upon at least one vertice with a degree of one.
Oh, so no. But under the examples, I
Oh.
mean, under the examples I gave you, there's no way to tell that isn't what it meant. But I guess I
Uh-huh.
should put another example, which would be like if we had some other weird city here,
Mm.
then this would still be a bridge. But
Ah, okay.
if I then did this, hang on, actually. But if I then did this, then this would no longer be a bridge.
Hmm. Okay. Hang on, let me erase this
And
line so I can more clearly look at this example where that's still a bridge.
yeah.
Um,
In fact, maybe if I actually visually erase it, then it will visually help. I feel like if I do, actually, you'll get it. So if that's not there, so this is a bridge, and this is what it looks like when we take it away.
oh, is it any edge without which the graph would become a disconnected graph?
Yes, exactly.
Okay.
Yeah, so it is like the bridge between two parts of land, right? Like if you take away a bridge between two islands or whatever, it's like then they're not connected anymore.
Mm-hmm.
So yeah, a bit more precisely, it's the so obviously like this graph was disconnected already because we had this Hobart thing, but it becomes in some sense
Yes.
more disconnected. So the way that we can talk about that is to say that um, well, I guess I need to introduce another term. So a term is a component, a connected component, or just a component. So in this graph, currently we have, I'll remove that other weird extra city too. Um, we have two connected components. We got
Mm-hmm.
Hobart and we got the rest of it,
Mm-hmm.
which I guess like makes pretty intuitive sense. But if we wanted to define that precisely, what we mean by connected component, it's any subgraph of the graph which
Mm-hmm.
is itself connected and is not a uh, a subgraph of a connected hmm, of a larger subgraph which is connected. That's very confusing with lots of recursions of subgraph though. So it's basically what's a clearer way to phrase that. It's a subgraph which is connected, and you
Mm-hmm.
can't if you want to find like a bigger part of the graph that contains the subgraph and that bigger part of the graph is also connected, you can't do it. So it's like the
Mm-hmm.
largest possible connected component. So for example, like this is connected and it's a subgraph, just to say these three. But it's not a
Mm-hmm.
component because you can also choose this bigger subgraph, which is also connected and contains it. So it has to be
Yeah.
the biggest possible one. Whereas this is a component. You can choose a bigger part of the graph, but like then that's disconnected. So like you
Mm-hmm.
can't. Yeah. Um,
Gotcha.
cool. So yeah. So a bridge is an edge where when you remove it, you increase the number of components by one. Yeah.
Okay.
So it goes from
Yeah,
a
cool.
having two components to having three components if we get rid of that. Yeah. Yeah, so it's a bridge. Which is kind of interesting in thinking about like a social network or something or some friend connection thing where it's like, oh, if these people didn't know each other, then they're like the link between two
Mm-hmm.
like friend groups or something. Um,
Yeah.
cool. Okay, so like I guess I feel like that's probably a thing that happens a lot where like say if two people start dating at the beginning, like their relationship is a bridge between like all the in like
Mm.
the graph of all of one of them's friends and all of the other friends. But then like as they're dating for a
Mm-hmm.
while and like their friends like meet the other person and meet each other and stuff, and then like that's no longer a bridge um because there
Mm.
are all the other connections. Yeah.
Yeah, cool.
Great. So it's bridge, as component. Um, then we have complement, and this is our last one before we have a fun task to do. So the complement of a graph. Uh,
Mm-hmm.
if we have a graph of, well, let's do verbal examples first. If we have a graph of like we had that graph last week of like all the characters in search party with the edges being if they've kissed.
Mm-hmm.
The complement of that graph would be the characters in search party and the edges being if they haven't kissed.
Huh. Okay.
Yeah. Or if we have this graph, then the complement of that graph would be a different color, would be this graph.
Mm-hmm. Gotcha.
So you have all the same vertices, but wherever
Mm-hmm.
there isn't an edge in the first graph, then there is an edge in the complement.
Aha, gotcha.
Yeah. So two vertices in the complement are neighbors, as in have an edge between them, if and only if they're not neighbors in the original graph.
Mm-hmm.
Flipping it.
Fantastic.
Yeah, that's the complement. Cool. Alrighty. So, time to prove something. Uh,
Uh-huh.
okay. Just thinking. Yeah, cool. Um, so we have a regular graph, which we can call G.
Mm-hmm.
So G is regular. Regular just meaning it is R regular for some value of R. So it could be 3 regular, it could be 4 regular. We don't know, but it is regular.
Uh-huh.
And if G is regular, then
Mm-hmm.
G complement is that
Mm-hmm.
necessarily also regular, necessarily not regular, or we can't tell. Sometimes it would be, sometimes it isn't. And then I guess
Ooh.
whatever your answer is, prove it. Um, I need to go to the toilet, so I'm going to give you a couple of
Okay.
minutes to think on this. Cool.
Great. I'm gonna talk to your recording while
Great.
you're gone.
Love that.
Okay, recording. So before I come up with a proof, I'm gonna do some examples just so that I can see if I can find out what is actually the correct answer before I do my proof. So let's see. Let's start with uh let's start with this. We've got 5 vertices. They're all gonna have 2 edges. Is that they've all got 2 edges. No, that one's got 4 edges. Fuck. Okay. Okay, that now has everything's got 2 edges. Okay, so the complement would be complement would be this one, this one, this one, this one, this one. Okay, so
I have returned, but don't
in
let me interrupt you.
that's okay. To bring you up to speed, I decided to do at least one example first, so I could
Great.
like
Yeah.
find out whether I can like find out what the answer is before I need to prove that it's
Yeah.
the answer.
Love it.
So in the blue edges, in the graph with the blue edges, that's regular. So now I think that I've drawn in the complement, which is oh, also regular, which is great.
Mm.
So that, and I think I've hit everything. I think everything's connected up. Yeah. Okay. Cool.
Yeah.
So let's try
So I
a
guess you can
different.
already ditch one of those 3 options, right? You know it can't be that it's always not regular.
Uh, yeah. So
Yeah.
it's going to be either always regular or we can't tell.
Yeah.
Um,
That's a
let's
fun
try another
general
example.
principle as well. Maybe I'll make that a teachable moment. Oh god, I hate that phrase so much. Um, when
What's the fun general principle?
well, that to disprove a conjecture just being like
Mm-hmm.
something we think is the case but haven't proved yet. To disprove it, all you need is
Mm-hmm.
one counterexample. So to prove it, you need like I'll prove like we did last week, where you have this whole set of reasoning. But to disprove it,
Mm-hmm.
well, to be more specific, to disprove a conjecture which is like of the form like all for all x, y is the case or whatever. To prove that's not the
Mm-hmm.
case, you just need a single counterexample, and that is, and you're done.
Mm-hmm.
Yeah.
Yeah.
So it's
I think I'm forming the point of view that is if the graph is regular, then the complement is also always regular.
Cool.
The maximum degree of every the maximum possible degree of each vertex in any given graph is the same. And therefore, if a certain number of degrees of that are taken up in the regular graph, then the same number of possible remaining degrees remains on each vertex.
Mm.
So in the complement, those are the degrees that will be filled in.
I agree.
That's my proof.
Yeah, great. We worked it out. Let's like make that slightly more precise in terms of like the terminology and what facts about graphs we're using and stuff. I agree that that holds, but I should actually find an example one of these weeks where because I feel like we say this stuff like proving like how um even if something holds for a few examples, it might not hold for everything, or how like being like really precise and the proof matters. But I feel like in the things we've done so far, it actually like hasn't mattered that much. Like the thing that you get the vibe of is true. So I should find something where it like really seems like something's the case, but then like when you have to get into it really precisely, you realize it's not. Because that's something that like happens quite a bit. So maybe I'll try and find some examples of that next week, which would be fun, kind of fun trick questions. But yeah, so if we were to phrase that. So I guess the parts of that that I think we can make more precise. I guess what do you reckon first would be the like parts of that that we can make a bit more precise?
Great question. I'll have to remember what I said.
Yeah, true. I guess this is the
maybe
downside of
maybe I'll
audio
just
proofs,
maybe I'll
the
just restate what
revolutionary.
I said, but take more care, and
Cool.
then we'll see if we're any closer. And maybe
Yeah.
I'll also try and like jot it down as I go. I'll get rid of some of this.
Cool.
Boop, boop. Okay. Let's make this. Okay. So, in any given graph, each vertex has the same max possible degree, being sum of the vertex minus 1. Wait, hang on. That's probably not well notated, but yeah. So in any given graph, each vertex has the same maximum possible degree, being the sum of all of the vertices minus 1.
What do you mean
So
by the
far, so
sum
good.
of all of the vertices?
The number of vertices in the graph.
Cool. Yeah. So that would just
Essentially, that's what I need to say. Being n number of vertices minus 1. Is that right?
yes. So for notation, you would just do I mean, you could use n if you said what n was, but if you don't want to have to do that, you can just do g brackets v, which is, sorry, v brackets g, which means the vertices of g, and then do those lines on each side to say that it's like the size of that set.
Minus 1.
Yeah.
Cool. Okay. So in a regular graph, each v has same degree. Therefore, in complement,
Oh, look at that little therefore symbol.
the oh gosh, go away, hang on. The degree of each v is how do I notate? Hang on, I'll just write it out in full. In the complement, the degree of each vertice will always be the r hang on will be VG minus R.
G minus R.
Like where R is the regular, like the regular degree from the graph rather than the complement.
Yes, except I think we still need the -1, right?
Oh yeah, -1 minus R.
Oh, hang on. Wait, is this right? -1.
Yeah, it is.
Yeah, because you just ignore it. Yes, it is. Thank you. Love the confidence.
Minus R. Is that right? So in any given graph, each vertex has the same maximum possible degree, being the number of vertices in the graph -1. In a regular graph, each vertex has the same degree, being R, and therefore in its complement, the degree of each vertex is that cardinality of the vertex set -1 minus R.
Yes, I think all of these statements are in fact true.
Mm.
Uh, the I reckon so. Yeah, I reckon there's a couple things that we can probably clean up a little. What do you reckon follows the least, or something? I mean, I feel like a useful way to think about this when you're like doing this with a proof, where you've kind of written something and you're like, oh, like how solid is that? Is this? It's like think of it less in terms of like, oh, like what is kind of not meeting the standards of like looking nice enough or something, but more in terms of like, okay, if like this wasn't right, if I kind of had fooled myself and then actually I was missing something, like where would that be?
Mm.
You know, like which parts of this is kind of would it be the easiest for to be like, oh, actually that doesn't follow or something. Does that make sense?
Mm.
If
Yep,
you're
yeah,
trying
yeah,
to,
that
if
makes
you're sort of
sense.
checking your own workings, yeah.
I feel pretty strongly confident about everything above this line.
Mm.
I don't think that's where the problem's going to be. Therefore, in the complement, the degree of each vertex will be that. Is there just a thing where it needs one more statement at the end being like, and therefore it like if every vertex in the complement is follows this same formula, then they're all going to have the same number and therefore regular? Is there like a missing step at the end?
Yeah, I think you would do the last thing where exactly you say something like that. You say like they are all regular with degree. This thing you've written, therefore they are regular by definition of regular graph or whatever. So that's like
Mm-hmm.
one little thing at the end. I also think this
Mm-hmm.
therefore is could probably be explained a bit more. Like I think you probably have that reasoning in your head, but you've said like to say
Mm-hmm.
therefore in the complement degree of each v is v of g -1 minus r. Like I don't think we've really said like
Mm-hmm.
why how we would know that would be the case.
Oh, does it? And do you mean like I would have to be like in a complement, like we have the opposite edges, and so if we have these edges in this graph, then like do I need to spell out a bit more what the complement is in order to then make this assertion?
Not necessarily saying what a compliment is, because I think you can like assume that. So you could say just like by the definition of compliment or something. But I think just going from like it
Mm-hmm.
would be kind of like why does it follow? Why does the fact that the maximum possible degree is this, and in R regular have this? Why does it follow that in the complement they're going to have this other degree?
Mm. Uh,
Or like how? Yeah, how do we know that that
okay.
follows? It could just be
The
like one
first
line. You know?
thing, yeah, the first thing that's coming, the first thing that's coming to mind is just to say the thing that you already said about like by the definition of complement, but like perhaps it needs to be like to specify a bit further. It's like in determining the complement, we can rule out like we can rule out this many. Hang on, no, sorry. We can rule out R edges, which leaves us with like this many other edges. No, hang on. That's not right. Therefore, okay, in a regular graph, each vertex has the same degree. by the definition of a complement. I'm stumped. I'm not sure how I would spell that out more clearly.
Should I tell you how I would do it?
Yeah.
Cool. Let me think. So, in a regular graph, each v has same degree r. I think I'd say something like so we've got the fact that edges exist in the complement only if they don't exist in the other one. So what would I say? So I'd say for the set of I guess I'd say something like the set of possible edges. There might be a quicker way than this, but maybe I'd say like so the set of possible edges. We could say A is the set of possible neighbors of this V, which I guess you could so it would be like say that's a U. I'm using my trackpad in my mouse. I'm like, why is this so much slower to draw? So it's the U in vertex set of G. Oh, it looks so messy. Such that U is not V, which is the set of possible neighbors. And then I would say for every U in V, I'm using symbols just so it's quicker to draw, but it's better to use words. That symbol just means for all. So for all U in A, I guess I could have just done that. I could have just said for all U that doesn't equal V. Anyway, we'll just say for all U in A, if hang on. No, I'm so confused. So we're saying if great. So I guess we can say then they have maybe I won't try and write it. But I think we'd say something like they are neighbors if and only if they are not neighbors in they're neighbors if and only if they're not neighbors in G. And I'd say the number of vertices that are not neighbors in G is the number of vertices minus the number of neighbors, which is Vg minus 1 minus r. Yeah, because I gotta make that shorter. Yeah. The number that are not neighbors is the total number minus r. Something like that. That was very precise. Yeah, so we're just stating, it's going to be the number that are neighbors is going to be the number that aren't neighbors in G, and the numbers that aren't neighbors in G is the total number minus the number that are neighbors, which is the total number minus r. Just laying out a few steps, that kind of thing. Cool. There's also a couple other little things, just sort of more pedantic things to make sure they're precise. So we've said in any given G, each V has the same max possible degree. But if G is a graph, then they don't actually have a max possible degree. They just have a degree, right? Like if we're taking an existing graph, they already just like have some degree. So So I think we like what we'd actually say is like for any given I think we'd say we just talk about the vertex set. Or we'd say for any given G, consider like the vertex set V of G and then each V has the same max velocity degree. Yeah, so it's just like a little pedantic thing. And yeah, we would just want to say, when we're saying like V or referring to V, we just say what we mean. So we'd say like HV in the vertex set of G. Yeah. That's it. Cool.
Great.
Great. So we know that if the G is regular, then the complement is also regular. Yay.
Yeah.
Let's do another fun definition, and then we'll have a theorem from that. So this fun definition is bipartite, which I feel like is like a fancier graph definition than the ones we've done so far. I don't know why. It feels more meaty or something. It's like, yeah, there's parts, but like bipartite. Maybe just because the word sounds fancier. The other words are like words which already exist, but then just giving math definitions, like connected or like bridge. But bipartite is like, what's that?
Spicy.
Spicy. Great. Bipartite, let's do some examples. So, I think you're erasing what I'm drawing. Maybe there's a delay.
Oh no! Yeah, there's a delay. I erased all the stuff ages ago, but I guess you just have to wait for me to be done.
Oh, that's so funny. Oh wow, the delay is not just in my display. It must be like in our actual interaction. Yeah, because like your old. Oh, and then my stuff that got erased reappeared. This is wild. Let's redelete. So a bipartite graph. Cool. This is like a quite, I would say, like a non-equal example of a bipartite graph. And this is a separate graph. Another one would be this. The bipartite graph. As you can probably see, it's like a bit of a more complicated concept. It's maybe is not intuitive yet, like what this is. A thing that could be like a sort of real example, something that might be a bipartite graph, would be like in a society where there is only heterosexual marriage and no legal gender reassignment. I was going to do a tweet. Maybe I did do a tweet the other day where I was like, I can't remember what it was. Some joke about how about how so many math examples are like maybe I said something like the worst thing about. Oh no, I know the joke was. The joke was like the real queer agenda is just like ruining all math plus examples because it's always like the probability is like so. A couple has a 50% chance of having a boy, 50% chance of having a girl, and so da 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 da. Or it'll be like, there's people like imagine a series of people that might get married to each other, and it's like is assuming that there's like men and women and they're all straight, and like there's so many just examples that use this like sort of gender binary as like a handy example for things that like have these two categories that interact in certain ways, which really is ruined by queer agenda. But if we imagine a society that is not exactly this, then the graph of marriages between people would be a bipartite graph. So not just current marriages, but like all marriages. So it could be multiple marriages. So these we can actually see both of these graphs we could interpret like this, right? So say if we look at this first one on the left, say if this is men and this is women, and like these two men would both be married to that woman, and this man's be married to that woman. And same thing, like this is women. So bipartite is obviously something about it being divided into two parts, right? It's like the men part and the women part. But what do we actually mean there? How can we kind of make that precise? It's like, I'll give you a second to think about it. I think it's probably would be pretty hard to come up with this one, but I'll still give you a moment just to marinate.
I have a feeling. Okay, I want to try.
Cool.
A bipartite graph is a graph in which there are two subsets of vertices wherein, like, in each subset of vertices, there are no edges between the vertices in the subset. There are only ever vertices that bridge that connect. There are only ever edges that connect a vertice in one subset to a vertice in the other subset.
Yes. Love
Love
it.
it.
That is the definition, basically. Yeah. It's
Yay!
saying two subsets. The only, hang on. Do we need to add any little fiddly precision bits to that? Let me see. Yeah. So just two little fiddly things. One is that we say, which actually isn't like clear from these examples, but we decide to make it so that it only counts if they well, this is actually, it depends on like there's different definitions of bipartite, basically. So it depends who you ask. Like, for example, the definition on Wikipedia is different from the definition used in my graph theory class. So basically it's just about whether you count, it's about whether the sets have to be disjoint. Meaning, do you know what disjoint means?
Nope.
It just means like non-overlapping. So like if this is a set of things, then like that set and that set are disjoint, but like that set and that set are not disjoint.
Gotcha.
Yeah. So it just means there's nothing that is in both sets. So some definitions don't specify that it has to be disjoint. And if it doesn't have to be disjoint, then the trivial graph, which is just one vertice, would be bipartite, because we can define two subsets where the first subset is this, and the second subset is also this, and there's no edges between members of the same subset. And on that definition that counts, but for the definition that we're using for my subject, which I guess we'll also use here for convenience, is that they have to be disjoint, which just means that like the graph will have to have at least two vertices in it for it to be possible to be bipartite. But yeah, basically it's exactly what you said, just that little tweak. Bipartite. Cool. So we can do a fun little theorem about bipartite graphs. I think I will not phrase this as okay. I would just like explain why it's the case. As opposed to using it as a challenge. So a graph which is not the trivial graph or the null graph, because we know that those can never be those aren't bipartite, so we will like ignore those. But for any other graph, it is, if it is bipartite, then it has no odd cycles. An odd cycle being a cycle of odd length. So hang on, I'm just getting a delay here. No odd cycle. And
wait, if it's bipartite, can it have any cycle?
Good question. Draw me an example of a bipartite graph which contains a cycle.
Which contains a cycle, but I can't, because you're not allowed to connect two members of the same subset. Hang on. Yeah, no, I'm not seeing it. I'm not seeing it. I just don't think. Hang on. I will try.
It can't be. Remember, it can't be an odd length cycle. So try to find it even length.
Yeah. Is that a did I do a cycle?
Yeah. That's a cycle, yeah. I mean, I guess, you can also check for yourself. So on our definition, does that meet the definition?
Cycles.
If you noted it down.
Walk between at least 3 vertices, which ends on the vertex it starts and doesn't hit the same vertex twice. Yeah.
There you go.
Great.
Yeah. But you observe that this is an even cycle, right?
Yes.
Yeah. And so it can't contain an odd cycle. And the other cool thing is that any graph, which is not a trivial graph or the null graph, and which contains no odd cycles, is bipartite. So it goes both directions. Yeah.
Mm-hmm.
Which we can write as and so the term that mathematicians use for this, which is a fun term, is that it characterizes that having no odd cycles characterizes bipartite graphs. And what characterizes means is basically that it's almost just like another way of defining it. So you have a definition for something, and then a characterization is like another condition which applies to everything in that category and only to things in that category. So it's like an equivalent definition. So it's like you could say that like even numbers are like numbers that you can divide by 2 and get an integer. But then you could also say like even numbers are integers which are adjacent to an odd number. That's true for all even numbers, right? And so that like characterizes even numbers. It's like an equivalent way of defining it. And some textbooks would like actually define bipartite as like a graph with no odd cycles. Because it's equivalent.
Mm-hmm.
So I will quickly I think I will just briefly explain this rather than prove, so that we can do a little more before we finish. Just try to get it to a level where it seems intuitive. So I guess like the no part was obviously already intuitive because at first it seems like it would have no cycles at all. So I guess it's the like having odd cycles that is more. Obviously there's two directions to prove here, right? So we've got oh my mouse is now being weird. I've got a delay on my screen. This is very strange. Okay. Maybe I'll speak more verbally. So when we're just a little proof note, when you want to prove something like this, which is, so we're saying that like we're saying that the graph is bipartite, non-null, non-trivial graph is bipartite if and only if it contains no odd cycles. If and only if is like the same as saying that like A implies B and B implies A, they both apply each other. So no odd cycles implies bipartite, bipartite implies no odd cycles. And when you want to prove that these things are like equivalent, you have to do that in 2 parts. So first you prove that like a graph with no odd cycles will be bipartite, and then you prove that a graph with bipartite will have no odd cycles. And then you've got both directions. So you have to prove each direction separately. Mostly, they can sometimes do it like that if you can just do it through like a chain of equals or something, but usually you need to do it separately. So if we start with bipartite and try to show we'll have no odd cycles, the kind of rough, not quite proof, but maybe makes it more intuitive, is that like, so you've got these 2 parts, and there's no edges between the parts. So if we, no edges between members of the same part. And so if there was an odd cycle, then that would mean this is the simplest way to make it intuitive. So you start on some vertex, which say is in part A, and we can say it's in. So we can do that without loss of generality. The terms that I mentioned in the email could be in A or B. So we just make it in A without loss of generality. And then we go to when we go to a vertex. Like when we follow an edge to another vertex, that vertex is going to be in B, right?
Mm-hmm.
And then we follow an edge from B to another vertex. If there is one, then that next one's going to be in A. and this goes on, right? So, and then if we number these vertices, so we number the first one as like 1, and then the next one is 2, and the next one is 3, etc. Then all the odd numbered vertices are going to be in A, and all the even number ones are going to be in B, right? Yeah. So that means if we eventually come back to A, which is a odd numbered vertice. Hang on. We start with 0. Yes, we're meant to start with 0 because that's how we number it. 0 is even. So we'll say like 0. So the first one is 0. So even numbers in A and odd numbers in B. 0 and then 1 in B, 2 in A, etc. So then if we come back to V0 where we started, the vertex before that, Vn, we know that vertex has to be in B because there's an edge between it and A. Between it and V0. Does that make sense? Yeah. And because it's in B, we know that it has to have an odd number. And hang on. Wait, it doesn't make sense. Wait. Oh, yes. And because of how we define cycles, like if n is odd, then it's an odd cycle. Yeah. Don't know how much sense did that make?
That made some sense. I have a question. So, a bipartite graph contains no odd cycles, i.e., any if we can define a bipartite graph as a graph containing no odd cycles, then it would seem to follow that a graph containing no cycles at all will necessarily be bipartite in the sense that it is true that it does not contain any odd cycles.
Exactly.
Is that the case?
That is the case.
Yeah. Okay.
Yeah. Love that. Cool. Okay, so that's bipartite is only with no odd cycles. Okay. Should I try to get through a few more categories or just give you a problem to do? I think I'll just.
If we were intending to end at 10, I'd have 3 minutes to do the problem. I'm obviously not going to make it a hard 10, but probably.
Yeah. Oh, yeah, no, hard 10's fine. We can do hard 10. Okay, maybe I'll just go through a few more things and then we'll give you a problem for homework.
Oh, cool.
So, bipartite. Okay, let's see if we can get through all these things in the next 3 minutes. This is a fun challenge. So we have. While my mouse is playing out, let me refresh this page. Why my computer being slow? Oh no, my computer's about to me out. Hang on. Okay. So if we have oh my god. What are you doing, computer? Okay, can you draw two vertices with an edge between them?
Yeah, this is great. Hang on.
Cool.
Clear out the. Okay, two vertices with an edge between them.
Yeah.
Boom. It'll have a delay, but it should show up on your screen eventually.
Great. Cool. So this is an edge, which you can call E. And then if you draw a vertex in the middle of that edge. So now we have 3 vertices and 2 edges.
Mm-hmm.
And that is, we say that what we've done there is subdivided that edge. That's what the term subdivide means. Just like add another vertex and turn it into 2 edges. And a subdivision of a whole graph is where you just do that to every edge in the graph. So you add a vertex in the middle of the edge. Fun fact, any graph which is a subdivision of another graph is going to be bipartite because you just define the first set A is all the original vertices and the other set B is all the new vertices, and every edge is going to go from an old vertex to a new vertex because you've inserted new vertices in between all of the old vertices so they don't connect anymore.
Cool.
Then we'll Okay. A Peterson graph. Great. We're just going to end on this like very random specific graph. This is a fun way to end. So yeah, we'll do hypercubes. So a hypercube, just because it sounds so cool, right? So a cube, if you draw a graph that has, if you draw a graph,
Do you want me to do this on our shared whiteboard?
yeah, cool. So imagine you've got like three, say there's like three things. Say like a dinner that has three possible ingredients you can use. Like you can use bread, and you can use tomatoes, and you can use jam. It's a very weird dinner. And if each vertice represents one possible like dinner, so one of it is like bread and jam, one of them's like just tomatoes, one of them's all of them, etc. So there's going to be 6 different ones, because there's 6 different combinations, which actually uses the same formula we use to find the maximum number of edges. It's that combinations formula that you used for the number of possible 2 active pairings to be on the movie poster.
Yeah.
When you have 3 things that can be present or not. And 2 of them. Oh no, sorry, that's not true what I just said, because it's not just 2 pairings. So it's actually going to be 8 possible. It's going to have 8 possible pairings, because each ingredient can be either present or not present. And so you like, with one ingredient there's 2 options, with 2 ingredients there's 4 options, because there's 2 times 2. And then with 3 ingredients there's 8 options, because there's 2 times 2 times 2 options. And then in a hypercube, there's an edge between any 2 of these options if they are only different by one thing. So it's like if you can go from one to the other just by changing one thing. So for example, like has all of them is going to be adjacent to has all of them except tomato, and to has all of them except jam, and to has all of them except bread, but not to has only jam, because you have to change, like you have to take away 2 things to get to that. So it's like all the other options you can get to by just taking away or adding a single thing.
Yeah.
And it turns out that if you draw these edges, you get a cube.
Oh.
Yeah. So you can think of the cube as like a diagram of like if you have three options and you're just changing, like 3 items and you're just adding or taking away a single one. It's like pathways through that cube. And then we just generalize that concept to higher dimensions, where like, what if you have 4 options, and then we call that thing a hypercube, which is a 4-dimensional hypercube, which is like the equivalent of a cube in 4-dimensional instead of 3-dimensional space, which is pretty wild. And then hypercubes, yeah. So it's like a graph thing, but also just like a kind of geometry thing, where it's like, if you're in like a 10-dimensional universe, then your equivalent of a cube is a 10-dimensional hypercube. Which would have how many edges? It should have 2 to the 10 edges, which is, I don't know what that is, but it's a large number. What is 2 to the 10? 2. Google. 2 to the power 10. If you're in 10-dimensional space, then your cubes have loading. Your cubes have at 1,024 edges. Crazy times.
Oh.
Yeah.
Hang on. In the dinner thing, why are there 8? I'm just drawing it out on our shared board. I've got the option. You said there's 8 options. There's bread, jam, tomato, bread and tomato, bread and jam, tomato and jam, bread, tomato and jam. Is the 8th option nothing that you just don't eat?
Yes, nothing is an option. Yeah, exactly.
Wow. Okay.
Yeah, I guess it's kind of strange to have an option. But I guess
But
that is sort of general principle in math stuff. Like whenever you define a thing, there's always one of the versions that's just going to be nothing. Like how a graph with just like nothing is still a graph.
And so, like, does bread and tomato to bread and jam count as something you draw, because you have to both remove tomato and also add jam? That seems
exactly. So you're not exactly. So that's 2 things. Yeah.
Okay. Fantastic. So those connect. those connect. Jam. Yeah, this is a wacky looking cube.
Yeah. It's a cube.
everywhere.
Someone's taken a cube and pulled apart all the edges. But if you
No one ever saw a cube like this before.
oh my god.
Are you seeing what I've drawn?
Crazy cube I am. Yeah. I'm just imagining you showing to someone and saying, "Look, I drew a cube." It's just like all these lines, and then just says like bread, tomato, bread and tomato. You're like, Georgia, are you sure that Jalen's been teaching you math and not just slowly driving you insane?
Me trying. Yeah.
But yes, I promise that if you move these vertices around, it will become a cube. And you can also take a cube and then like label the vertices in this way so that it holds and they are connected. Yeah. So that's that. Yeah, so I guess this time we more just like I more like listed things and there wasn't as much like proving things. But yeah. How was the like whirlwind of definitions?
No, it's great. I feel like I want to do more than one problem because I feel like I want to apply things. Definitely do the same approach of like send me the one problem that I have to do and then some others that are optional because I'm expressing a lot of enthusiasm now, but I'm also, you know, hanging out with my family and, you know, trying to have a life and stuff. But yeah, I'm excited.
Yeah. Should I even
send this into practice?
Should I like send you one and then like when you send me answer, then I send you another one? Or should I just attach other ones at the start?
You are like right on schedule, starting to break up. I think you just. Oh, okay. I think you just asked whether you should send the problems one at a time or whether you should send them as a group. I think. I think send the do it the same way you already did.
Cool,
the one that I have to do, and then like send all the other ones at the same time.
Great. Will do.
Yeah.
Alrighty. Well, there you go. We got through most of week 2 of graph theory. There you go.
Yay! Graph theory!
Yay! Next week is going to be very fun. Sneak preview next week is next week we're going to learn how to take any graph, like a graph of like cities and railways, and find, starting from any like city, find the shortest route to every other city, like an algorithm to find the shortest path between 2 points in like a graph.
Great.
Yeah,
I love
Google
it.
Maps style. We'll be our own Google Maps.
Very exciting.
Cool. Well, sleep well
and
have a great. Oh, have you already been doing the? When did you get up there again? Have you already been doing the sessions?
Yeah, we've done 2 already. There's a third one
cool.
tomorrow.
How's it going?
There's 3 more next week. Yeah, so far so good. Having a good time. Wednesday was a bit hard going just because I was very, very low energy. But Monday was great, and I'm looking forward to tomorrow.
Cool. Well, enjoy. I'll let you get some sleep.
Yeah.
And I will send that problem.
Great. Thanks, Jalen.
Cool.
Have a
Thank
good week, you too, and have a good weekend. And I'll see you next week.
Cool. See ya.
Bye.
Bye. Ooh.